Hey guys, this is 5.5 from pre-calculus, and this is how to solve a trigonometric equation. You guys have been solving equations, solving for x, since back-end algebra. Now we're going to see how that works when there are trig functions in the equation. Okay? This section is very important to solidify for calculus. Okay? And in order to succeed in this section, you have to make sure that you have watched and understood 4.7 from pre-cal. Okay? So when I give you these equations, step one is going to be to isolate the trig function. Once the trig function is isolated, then I'm going to use what I learned in 4.7 from pre-cal and do the inverse trig function. Okay? Once I've done that, that's going to be used to isolate the inside. Like if it's sine of 3x or sine of x, we're going to isolate that 3x or x. Once we've done the inverse trig function, we need to include a plus 2n pi for sines and cosines, or a plus n pi for tangents, where n is going to represent a number of rotations in our unit circle. Okay? So our step 4 is going to be to isolate x. If, when we took step 2 and 3, x was already isolated, you do not have to worry about step 5 getting more complicated. And I'll show you that with a simple problem and then as we move on to more complicated problems. Okay? So after we isolate x, now we're going to test different n's starting at 0 within the domain. So usually the questions will tell you that they want it to exist from 0 to 2 pi. Okay? So we're going to test our answers. Once we get something that surpasses 2 pi, we stop. We want all of our answers to be values in between 0 and 2 pi. So let's see how this works. Okay? Here's my first equation. 3 sine of x equals square root of 3 plus sine of x. And my domain is from 0 to 2 pi. So step 1 is going to be to isolate the trig functions. So I've got 3 sines here and one of them over here. So I'm going to subtract the sine from both sides. This one cancels. 3 sines minus 1 sine, it's going to give me 2 sine of x equals square root of 3. Okay, I still haven't isolated that sine. Now I'm going to divide that 2. So sine of x equals radical 3 over 2. I am done with step 1. I have isolated my trig function. Now, in step 2, I'm going to use inverse trig functions. So the way I isolate x is I ask myself the inverse sine of square root of 3 over 2. So just like back in algebra, whenever we wanted to solve for x, we did the inverse operation. Like if I had a plus 3, I subtracted a 3. Like here I had a positive sign, I subtracted a sign. The inverse operation of sine, how to isolate it from the x, is literally just, oops, I forgot my little one, inverse sine of that value. So now in 4.7, I know that for sine, I use the right side of my unit circle. And sine of x is equal to radical 3 over 2 at pi over 3. And also, if you keep looking at the entire unit circle, which I'm allowed to do here because they want me to check the entire from 0 to 2 pi, also at 2 pi over 3. Okay? So I am done with step 2. Step 3 says to include a plus 2n pi for sine and cosine. This was a sine question. So I'm going to add plus 2n pi. N is a variable, taking into account multiple times that this can happen. So the reason why it could happen multiple times is if my initial function had a stretch or a shrink, I can have more values within that domain. Okay? So at this moment, once I have isolated x and I have my 2n pi, we're going to call this our general solution. Okay? Now my particular solution, my exact answer, is going to be when I test my n's. So we always start if n were 0. If n were 0, then 0 would multiply all of this out and all of this out. I would only have that x is pi over 3. And 2 pi over 3. Okay? Well, you know what? Let me pause on the boxing. So now if I test that n is 1, 1 times 2 times pi is 2 pi. Hopefully you start catching, I hope you agree, that if I add a 2 pi to some value, I'm definitely going to pass 2 pi and I'm going to get out of my domain. So one more time, if n is 1, this gives me 2 pi. If I add 2 pi to any positive value, I'm going to surpass it. So anytime that you isolate x, isolate the inside of the trig function, and x is already by itself, know that anything past 0 is going to be too big because I'd be adding 2 pi and getting out of my domain. So my only answer would be when n is 0, and I can call this my particular solution. Okay? Up next, I'm going to show you an example where you do have to keep testing because x is not by itself here. On this next question, we have 2 sine of x over 2 equals 1, and they want my domain to be from 0 to 2 pi, including 0. So step 1, isolate the trig function. I do that by dividing this 2 away, and I'd have sine of, you can call this x over 2, or you can call it half times x. Either way, it still works. So if I divide that 2 over here, I have 1/2. Now that I have my trig function isolated, I can move to step 2 and do the inverse trig function. So the way I move that sign out is I say x over 2 equals inverse sine of 1/2. Okay, I'm going to leave this left side alone for a moment. I'm going to answer this inverse. When does sine equal 1/2 on my unit circle? It happens at pi over 6, okay? And it also happens, I'm going to write down here, at 5 pi over 6. And I'm just going to rewrite this x over 2. Now for sine functions, remember step 3, we need to include a plus 2n pi. Okay, so notice because it happened twice on the unit circle, I am solving this 2 different times. Okay. Next step is to isolate x. I am dividing by 2 here, so I need to multiply by 2 so that these can cancel. Make sure when you multiply by 2, it is being distributed to both terms. Okay. So now we have that x equals 2 pi over 6 plus 4n pi. Okay. And then for the bottom one, when I multiply it 2, we get 10 pi over 6 plus 4n pi. Okay. If you'd like to see this reduced, we can say that x equals pi over 3 plus 4n pi, and x equals 5 pi over 3 plus 4n pi. At this point, I have my general solution. I'm going to put a GS for general solution, save some time. And now I'm going to come up here and test my n's. So when n is 0, 0 will, we'll use this one, the reduced one, just so our values are more recognizable from the unit circle. If I plug in a 0 into n, these entire 4 pi's cancel out, and x is just pi over 3 and 5 pi over 3. When n is 1, 1 times 4 pi is 4 pi. If I add 4 pi to any positive value, I am definitely going to surpass 2 pi, so that becomes too big. All right, so in this case, we still didn't need 1. And we only have 2 values in our particular solution. All right, let's let them start getting a little more difficult. I want to start showing you some questions that when you first look at them on your own, you probably wouldn't think of doing this. So I'm going to show you some things that are out there. If I have this question, I can't separate each of them equal to 0 because it's not separated by multiplication. And one thing I could do is move the cosine over, but then I'd have a negative cosine. And then you're asking yourself, when in the unit circle does a positive sign equal a negative cosine? You could also square both sides. We have different options. So I think the easiest one here, of all those options I just mentioned, would be to move one of those trig functions to the other side. So let's say I subtract my cosine to the right side. Pause this video, open up a unit circle on Google, and ask yourself, when do sine and cosines have equal values but opposite signs? One more time, when on the unit circle are sine and cosine equal in value but have opposite signs? And hopefully you can see that happens when there's a positive and negative radical 2 over 2, and that happens twice in the unit circle, okay? That happens when my value on the unit circle is 3 pi over 4, okay? There we have radical 2 over 2, radical 2 over 2, with one of them being positive and one being negative. And it also happens at 7 pi over 4. Now remember, for sines and cosines, we add the plus 2 and pi. And because x is isolated, this is already our general solution. So this one didn't have much work for isolating, but it did make you pause and really think about these values on the unit circle. Your unit circle is your best friend, guys. The more you have it memorized, the easier this becomes. So now I'm going to test out when my n is 0. This right side cancels out, and I just have that x is 3 pi over 4 and 7 pi over 4. When n equals 1, I'm adding a 2 pi, but anytime I add a 2 pi to a positive value, I surpass 2 pi. So these become too big. Okay? Let's take a look at this next question. I have a lot of students who make such a common, simple mistake on this one. So I'm going to show you 2 ways to solve this one. Most students, when they see this question, they want to divide out a sign. Okay? If you divide out a sign, these 2 cancel, and these 2 cancel, and you end up with tangent of x equals 1. And you can finish this, but you would have some of the correct answers. You wouldn't have all of them because you eliminated this sign. So if you like dividing out the sign, the rule of thumb is that if a trig value gets completely eliminated by dividing out, you must also say that that one, because it got eliminated, equals 0. Okay? Now, let me show you how and why this works, not by remembering some rule of thumb. Okay? The other option would be to subtract this sign to the left side. So I have sine of x times tangent of x. I'm subtracting this sign to the left equals 0. In this point, there's a sign in both terms, so I can factor out that sign and say tangent of x minus 1 equals 0. Whenever 2 values are being multiplied, you can set each of them equal to 0. And now I have sine of x equals 0 and tangent of x minus 1 equals 0. And to finish isolating the trig function, here we're good. On this one, I'd have to say, okay, tangent of x, I'm going to add that one over, equals 1. And notice that I end up with the sine of x equals 0 and the tangent of x equals 1. So 2 different methods, okay, giving you the same exact thing. Okay, so either way that you did it, now we just finished solving both, whether you're here or whether you're here. So now that I have the trig function isolated is when I'm going to use my inverse operations. Okay, tangent equals 1 when x equals pi over 4 in quadrant 1, and also f5 pi over 4 in quadrant 3. With tangents, we have to add n pi. Okay? Now we're going to do the same thing for sine of x equaling 0. Sine of x equals 0 when x is 0 and when x is pi. Okay? Oops, let me write it underneath so we can add our... And then for sine, we add 2n pi. And this right here, guys, is our general solution. We have 4 of them now because of how those trig functions split up. And that's our general solution. Okay? So now I'm going to test my n's, and I'm going to say, okay, when n is 0, all of these that have the n's cancel out, and my x is, I'm just going to list them, pi over 4, 5 pi over 4, 0, and pi. Don't worry if they're in order, okay? Now I'm going to test when n is 1, okay? When I plug a 1 in here, I'm only adding a single pi, okay? When I'm putting a 1 in here, I'm adding 2 pi. So we've already come to the agreement that adding 2 pi surpasses 2 pi. Even if I add 2 pi to 0, I get to 2 pi, but notice that the inequality is not underlined. So I cannot include 2 pi. That's already too big. So I'm not going to be adding on this side, but I am going to try on this side, okay? So if I add on this one, I'm going to have pi over 4 plus 1 pi, and then I'm going to do it to the bottom. 5 pi over 4 plus 1 pi. I need to take a moment and get common denominators. So what I'm really adding is pi over 4 plus 4 pi over 4, which gives me 5 pi over 4. And if you notice, I already had 5 pi over 4 in my answer. So that's okay. This is still within my domain, but I was already including it in my answer, okay? Let's do the bottom one. 5 pi over 4 plus 4 pi over 4 gives me 9 pi over 4. Now you need to ask yourself, is that bigger than 2 pi? Well, ignore the pi's for a second. Is 9 over 4 greater than 2? Well, if that numerator was an 8, 8 over 4 would give me exactly 2. Because it's a 9, it's greater, which means this is going to give me 2 point something, and this is too big. Once I get it too big, I stop. I don't keep going. And this 5 pi over 4 did work, but I don't have to worry about adding it to my answer because it was already there. So this is my particular solution. This next question reads, tangent of 2x equals square root of 3. And again, we're looking from 0 to 2 pi. So we get to skip our first step here because the trig function, which is tangent, is already isolated. It doesn't have anything being added to it or multiplied to it on the outside. Okay, inside parentheses does not count. So now I'm asking myself, when does this trig function tangent equal radical 3? If you want to take the extra step to write the inverse, go for it. I'm going to bring down this 2x equals inverse tangent of radical 3. And again, this is where being solid on your unit circle and 4.7 of pre-cal is really going to come in handy, because I can quickly off the top of my head say that tangent is equal to radical 3 at pi over 3. And that's me solving the right side. I'm going to bring down this 2x on the left side. Okay. remember, my next step before isolating the x is to add a 2n pi for sine and cosine and to add an n pi for tangents. Now I can move on to isolating the x, which if I'm multiplying by a 2, I'm going to divide by 2 on this side and divide by 2 on this side, which is the same thing as multiplying by 1/2. So x equals, if I multiply here by half, I end up with pi over 6 plus n pi over 2. Okay? Once I have my x value isolated, this right here is my general solution. It's what I'm going to use to get my actual answers, my particular solutions. Okay? So now let's start with our testing. We're going to start with n equals 0. When n is 0, this entire thing cancels out, and I just have my pi over 6. When n equals 1, I am adding pi over 2. So I have pi over 6 plus pi over 2. I'm going to need a common denominator. So I'm going to multiply by 3 over 3. And what I'm really adding is pi over 6 plus 3 pi over 6, which gets me down to 4 pi over 6. I'm going to ask you not to reduce yet. It's going to make the rest of your problem easier. Remember, you stop when you pass 2 pi. Anytime you are talking about a fraction, ignore the pi's for a second. 2 is equal in a fraction when the numerator is double the denominator. For example, 4 over 2 is 2. 8 over 4 is 2. 10 over 5 is 2. So if my denominator is a 6, I'm looking to stop once I pass double my denominator. So the moment I get double 6, which is 12 or anything greater on the numerator, that's when I'm going to stop and I'm too big. So far, pi over 6 works and 4 pi over 6. Again, once that gets to a 12 or bigger is when I'm stopping. So when n equals 2, I am adding another one of these increments. Now, you can sit here and keep doing the math and say 4 pi over 6 plus another pi over 2, which is, and get common denominator in the whole thing. But know that I am going to add every single time another 3 pi over 6, because I added one here, and now I'm going to be adding a second one too here. So if I have 4 pi over 6 and I am adding another 3 pi over 6, 4 and 3 makes 7. Okay, so I'm going to walk through the slow motion here, but know that you can do that the fast version. Okay, so I have 4 pi over 6. I'm adding a second time my common denominator, which is 3 pi over 6, which gives me 7 pi over 6. Not at 12 yet, so this is good. Let's add for a third time. I'm going to get my previous answer and add another 3 pi over 6, 7, 8, 9, 10. I have 10 pi over 6. And again, don't reduce so that you can quickly see, quickly keep adding with a common denominator and quickly see when I surpass. So this is good. My numerator is still smaller than 12. When n equals 4, I'm going to get that previous answer and add a 3 pi over 6. 10 and 3 make 13. And hopefully this is a red flag because I was looking for my numerator to be double my denominator, which is 12. So this one is too big. So now for my particular solution, I can say that x equals, I'm going to go down the line here, pi over 6, 4 pi over 6. You can reduce or not. I really don't mind. If it's a multiple choice, just be vigilant of it. 7 pi over 6 and 10 pi over 6. Okay, so I'm going to train you the same way an AP test would ask you for next year. And if it's free response, You can leave it as is. If it's a multiple choice, it will be reduced. Okay, so you would just reduce this to 2 pi over 3 and this one to 5 pi over 3. Okay? This next one is going to take us back to memory lane with a little bit of algebra. So you may not see it at first, but if I have a value squared plus that same value to the first minus a number, I technically have a trinomial here that's going to actually clean up really nice into two binomials like we used to see in algebra. So in order to help you visualize this, I'm going to take a moment and say, I'm going to rewrite tangent. And I'm going to rewrite tangent just with the variable x for a minute. Okay? I typically don't like to use the same variable that exists here, just because that can be confusing later on, but I think it's really going to help you visualize it. So if I replace the word tangent with an x, this tangent is squared, so I'm going to call this x squared. Plus, I'm going to replace this tangent with an x, and then I'm going to say minus 2. When you were solving regular functions back in algebra, this hopefully looked really familiar, and if you needed to solve for x's, you can catch, hey, I can factor this into two binomials. And I can say, okay, this is going to be an x and an x. Two numbers that multiply to give me 2 is going to be a 1 and a 2, okay? And then that combine to give me a positive 1. Well, if I want a positive 1, I need this 2 to be positive and this 1 to be negative, okay? Then I would go on to say x minus 1 equals 0 and x plus 2 equals 0. And then I could say x equals 1 and x equals negative 2. Now that I got that x by itself, I can put tangent back in place. I solved it in a way that seems a little more familiar. And I can say tangent of x equals 1 and tangent of x equals negative 2. And now I have my trig functions isolated. If you start to get really comfortable with these, you might even be able to factor this with the tangents and say that this would be tangent minus 1 times tangent plus 2. I have a degree in math and I still do it this way with my x's. It's just easier on the eyes. I think it's easier to see, okay? So now that I'm down to step 1 and I have my trig function isolated, I'm going to do my inverse trig functions. So inverse tangent of 1. I know that that on my unit circle exists, and it exists at pi over 4. And remember to always add your n pi. On this side, hopefully there's two different ways of seeing this. One is the fact that there are no negative 2 in my unit circles. Okay? It only goes up to positive and negative 1. And if you were to put this in your calculator, you would get an error to confirm it. Okay? An error on a calculator means that there are no values that exist. Okay? They do not exist. So my only general solution right here is this pi over 4 plus n pi. Okay, is my general solution. So now let's move on up to my next step. I'm going to look for my particular solutions. I'm going to start with n equals 0. When n is 0, this entire side cancels out, and x is just pi over 4. When n equals 1, I'm going to add 1 pi. I need to get a common denominator. And what I'm really adding now is pi over 4 plus 4 pi over 4. This gives me 5 pi over 4. Remember, I do not want to surpass 2 pi. And if my denominator is a 4, a fraction that gives me 2 pi would be double 4, which would be 8 pi over 4. So this is still less. We are still good. And of course, this one was good. So let's move on to the next one. When n is 2, I'm going to get my previous answer. And I am adding a second. Remember that this 4 pi over 4 is the same pi that I added, just with a common denominator. So I'm going to add another one. Hopefully this feels really familiar to when we were graphing trig functions and getting our 5 points. So 5 and 4 make 9 pi over 4. I surpassed that 8 pi over 4 that I was looking for, so this one is too big. Okay, so my only answers are pi over 4 and 5 pi over 4. And that is my particular solution. Okay? Okay, I'm going to leave you with 2 last questions, and I'm going to up it. I'm going to make it a bit more difficult. So bear with me. Just want you to be able to think out of the box with these. So looking at this next question, your first instinct might be to divide out that entire 4 to the other side, because our goal is to isolate these trig functions. Now, if I divide out the 4 to the other side, I'm going to have a square root of 3 over 4, which if my next step is to look to my unit circle, there are no square root of 3s over 4s. So my unit circle does have a lot of square root of 3 over 2s. So I'm going to start off like that. I'm going to divide both sides by 2. And then I'm going to end up with 2 sine x cosine x. And just me saying that out loud, I hope it seems familiar. If you are one of my students, you know that I am a stickler for you memorizing your formulas so that when you visualize and verbally say 2 sine cosine, that rings a bell, and hopefully you can catch that that is a formula you learned earlier in this chapter, and that it is sine of 2x. It is a double angle formula. And that makes life a lot easier because now I have my trig function isolated. Now I can go to my step 2, bring down this 2x, and say inverse sine of square root of 3 over 2. Now, sine is equal to square root of 3 over 2 on my unit circle at pi over 3 and also at 2 pi over 3. Okay, I'm going to drop down this 2x, and because it's a sine function, I'm going to add my 2n pi. Okay, so remember now I'm dealing with 2 of them because it happened twice in the unit circle. My next step is going to be, if I'm multiplying by 2, I'm going to divide by 2 on both of them. Now again, you can see this as dividing by 2 or by multiplying by half. Both work the same exact way. So here I end up with x equals, if I'm dividing by 2, the denominator gets multiplied, so I have pi over 6. Plus, and here dividing by 2 cancels this 2 out, just adding n pi. If I'm dividing by 2 here, it cancels out with that 2. Or I can call this 2 pi over 6 so that I keep a common denominator already. Different options, okay? And again, dividing by 2 here just leaves me with n pi. So I personally like keeping common denominators throughout the entire way so that my math is a little simpler. But again, if you would have written pi over 3 here, you still would be correct. I have x isolated, so now this is my general solution. I'm going to go on up and start testing my n's. When n is 0, these two cancel out, and x is pi over 6 and 2 pi over 6. If my denominator is 6 and I do not want to pass 2 pi, I want to stop when my numerator is double that denominator. So I want to stop when my numerator reaches 12 or above. So when n equals 1, I'm going to do one at a time. I'm going to add 1 pi. Okay? I need a common denominator. So I'm going to multiply this by 6 over 6. And now I'm saying pi over 6 plus 6 pi over 6. This gives me 7 pi over 6. I'm less than 12, so these work. Okay? Now, I did it to pi over 6 when n was 1. Now I need to do this to 2 pi over 6 plus I already did my common denominator once. No need to do it again. So 6 and 2 make 8 pi over 6. Still less than the 12. Let's keep going. When n is 2, to my previous answer, I need to do it for both. So to my previous answer here, I had 7 pi over 6, and I'm going to add my common denominator, which was 6 pi over 6. 6 and 7 make 13 pi over 6. I surpassed that 12, so this one is too big. Let's check the bottom one, which if it got too big for 7 pi over 6, I hope you can make the assumption that it's going to get too big for 8 pi over 6. But if you do the work, you're getting your previous answer and adding another pi, which with common denominator is 6 pi over 6. And you get 14 pi over 6. Again, surpass that 12 we were looking for in our numerator. So my particular solutions, I'm going to list them one at a time. Look for those check marks. We have pi over 6, 2 pi over 6. We had gotten 7 pi over 6 and 8 pi over 6. Make sure to stay organized with this work, guys. It's very easy to get lost. And this one is my particular solution. Our last question is sine of x equals sine of 2x. Again, same domain. I'm going to start off by getting these on the same side. So I'm going to subtract this sine of x over. I cannot combine them, which is why I wrote this a little over, because the insides are different. I have a 2x and an x here. So I end up with sine of 2x minus sine of x. And this side cancels out to 0. I'm just going to choose to write it over here on my right-hand side. Now, these trig functions you can't really keep on if the insides are different. So I'm going to use a formula from earlier in this chapter, the double angle formula, that will change this to all having the insides as a single x. So sine of 2x, I'm going to change to 2 sine x cosine x. And now I'm going to bring down this minus sine of x. Now everything is in terms of a single x. Notice that I have two terms and both of them have a sine of x in common. I'm going to factor that out. Factoring is always a great way to help us solve these functions. I'm left with a 2 cosine of x minus 1. Remember, whenever I am separated by multiplication, I can set each of them equal to 0. This left side, the trig function is already isolated, so I'm ready to go on this one. I have to keep going on this right side. I'm going to add the 1 and then divide the 2. Okay, so now that I have my trig functions isolated, I can keep going with the next step. Let's just keep everything lined up. I'm going to move that sign over and I say x is equal to inverse sine of 0. And here, x is equal to inverse cosine of 1/2. So on my unit circle, sine is equal to 0 at 0 and at pi. Because it's a sine, we're going to add our 2n pi. On my unit circle, cosine equals 1/2 at pi over 3 and at 5 pi over 3. And because it's cosine, I'm going to add my 2n pi. This here is my general solution because x is already isolated. Now when I start testing my n's, when n is 0, these 2n pi's cancel out and x is 0, pi over 3, and 5 pi over 3. Okay? Everything is, remember, double the denominator. My denominator is 3. Double it would be 6. Anything past 6 would be greater than 2 pi. And when n is 1, I'm plugging a 1 in here, meaning I'm adding a 2 pi. Anytime I add a 2 pi to a positive value, it's going to surpass or reach 2 pi. So that means all of my x's here would be too big. If you want to go through the motions adding them, you can. So that means that these are my only answers, and these are my particular solutions.